Okay, Ward, I think now we could start.
Okay, thanks. Thanks. Hi, also, it's a pleasure to welcome you to today's session in our series Laws of Nature. Before we get started, let me just say briefly a few words about this series. And let me pull up the website for that. So this series is an initiative initiated by Dirk Deckert, Angelo Bassi, and myself. And the idea is to promote the exchange of mathematical, physical, and philosophical ideas in the field of foundations of physics. And we have monthly sessions, and each session is themed differently. So today we have quantum gravity as the theme. Next month we'll have quantum foundations as the theme. And then we have a break, a summer break, until we start again in the fall. Okay. And for those that missed previous talks, you can always watch them online using these links here on the website, which brings you to the YouTube channel. With that said, let me give the floor to Paula Reichert, who will be chairing today's session.
Thank you, Ward. So welcome also from my side. Yeah, as Ward already said, we have a meeting here today on quantum gravity. And I'm happy that today we have two speakers who are experts in that. So we have first Francesca Vidotto, and then we have Stefano Liberati. And yeah, before we start, let me just outline the structure of today's session. So first, Francesca Vidotto is going to talk about 45 minutes, and then you will have time to ask questions. So we have about 15 minutes for questions. And then there will be the second talk, again 45 minutes, by Stefano Liberati, and some 10 or 15 minutes of questions to the talk. And in the end, we have a panel discussion where you will have the chance to ask general questions, not necessarily connected to the talks, but more general. And you can address both speakers and they will comment on it. So we have like half an hour in the end for that. Okay, so you will later be able to ask your questions by raising the hands. So you all know that, I guess. You have in the column below the option to raise your hands, and then I call you and you can ask directly. And if you have any question during the talk, please take care that this is only short question, technical question, nothing too general. Then you can write it into the chat and I will read it if it fits in the program. So to not interrupt the speakers for too long. Okay, so now I'm happy to introduce our first speaker, Francesca Vidotto, who is a professor at the University of Western Ontario in Canada. And she's most well known for her contributions to conformal loop quantum gravity. And yeah, the title of her talk is, if you want to build a universe from scratch, you must first invent a quantum state of the geometry. So we are very interested in that. Thank you. Please.
Thank you, Paola, for the introduction. And so let me share my screen. Yeah, I hope you are seeing it in a full screen at this point. Good. And so first of all, the title, I enjoy a lot of funny titles, but not always people get the references. So let me start from there, if I can.
If you wish to make an apple pie from scratch, you must first invent the universe.
So that was, of course, our beloved Carl Sagan. And so I took very seriously what he said. In fact, I have a poster in my kitchen that says so, just next to my oven. And so let's take seriously the question. We need first to invent the universe. Well, actually, in order to invent the universe, to make the universe, we kind of know how to do it, but this goes through some steps. And as the title of my talk says, I would convince you that you have to start with a good quantum state of the geometry. But first, let me use the help of this illustration from PhD Comics to remind you what would be the standard answer of somebody, possibly just cosmologist not interested in quantum gravity. So we have a story about how the universe started. The universe was hot and dense in the beginning. This is what we call the Big Bang. And in this regime, quantum fluctuations are wild. So the fields, the various fields that populate the universe, but including also the gravitational fields, fluctuating widely. And we think that these fluctuations are the origin of all the structures that we see in the universe. In particular, in the standard model of cosmology, the idea is that inflations takes these fluctuations and stretch them so that we obtain, basically they stretch inflation stretch them to what, to the older stage that we see in the universe, namely the CMB. And then from the CMB, from what we observe on the CMB, from the inhomogeneities that we observe in the CMB, nowadays we are able to reconstruct through simulations all the structures that we see in the universe, adopting the so-called lambda CDM scenario. Very well. The problem with inflation is that, well, first of all, we don't know what makes the universe inflate. So there should be a field, an inflaton field that we don't know about. You can be conservative, you can think that it's maybe the Higgs field, or but in most computation, people take an agnostic stand, just throw in this field in the computations. And this field drives the dynamics, that drives the expansion, and drives also the way in which fluctuation propagates in the universe. The problem that one has to face with this scenario is that, first of all, you want the proper initial conditions for the inflaton field, and in particular, you want the kinetic energy of the inflaton to dominate over the potential. And in standard cosmology, you have to put this information by hand. And the other information you have to put by hand is the choice of vacuum state. So this is the pivotal point that I want to discuss in this talk. Actually, if we include something, so the basic things that we have learned so far about the application of quantum gravity to cosmology, well, first of all, let me tell you that in loop quantum gravity, there is a prediction of a maximal bound for the curvature. So this means that as long as we are concerned with curvature singularity, and the Big Bang is indeed a curvature singularity, then these singularities are not there. Well, this is not very important for, well, it may seem not important in the sense that the Big Bang scenario doesn't address the problem of the singularity. In a sense, in the way in which I have presented it, I say that, so you have a primordial era that is hot and dense. You don't have to assume anything about whether there is a singularity there or not.
Francesca, may I interject here? Are we supposed to still see the first slide, or are you already on a different slide?
I am moving to a different slide.
Okay, so we see the cake of the universe at the moment.
No. this is not what you're supposed to see.
Could it be that you are
Thank you for letting me know.
Sorry. Yeah.
No, very good. No, thank you for letting me know. Of course, there was a lot of text. So let me stop the sharing, and maybe I can try to do the sharing in a different way.
Sometimes Zoom has problems with full screen mode.
Yeah, no, I have tried different things. So one thing that I can do is the following. Let's see if it works better. Okay, so.
Okay, I think.
Yeah, this is more a safer way. And these are the nice things you are supposed to see.
Thanks, yeah.
So this is the nice illustration by Jorge Cham with inflation, all the things I told you about the Big Bang, the inflaton field, and the initial condition. Okay, very good. We can resume from here. So please, I don't know, take a screenshot of this because I want to go ahead, because the next step is to move from this classical or semi-classical picture, the standard model of cosmology, to a picture that includes more information regarding singularities. And in particular, so I was telling you that in loop quantum gravity, we don't have curvature singularities, even though you may think, okay, is this important for the world scenario? Well, yes, in the following sense. First of all, well, instead of initial singularity, the most generic prediction, there are different possible models, but the most generic one is one in which instead of singularity, you have a big bounce. So the current expansion of the universe is in fact the evolution after a precedent contracting phase of the universe. So we have contraction, the achievement of a maximal energy density, so a maximal curvature, and then a new expanding phase. So you can think of this process as a tunneling between two classical solutions of general relativity, a solution in which the universe is contracting, a solution in which the universe is expanding, and then because of quantum gravity, we can do a tunneling between the two of them. Or you can think, I mean, picturing tunneling is always difficult. So if you prefer, you can think really in terms of this bounce. At the effective level, what happens is that it appears an effective repulsive force that forced the universe to start this new expanding phase. Coming back to the question, so how this changes the standard scenario of cosmology? Well, it changes the fact that, first of all, because of this contracting phase, inflation becomes generic in the sense that the initial condition of inflations, in which, as I said before, the kinetic energy dominates over the potential, is naturally achieved. So the contractions makes the inflaton potential, the inflaton field to climb its own potential. So in a sense, so quantum gravity is already making a nice job here, making inflation in a sense more natural. Nevertheless, one can, even using the techniques of loop quantum gravity applied to cosmology in the framework that is known as loop quantum cosmology, one is still have a problem regarding the choice of the vacuum. In loop quantum cosmology, one uses generic states. The states are not really derived from the full theory. They are you can think about generic effective states. And in particular, when it comes to choosing the initial vacuum state, here, well, there are different proposals, but it's still a matter of choice. It's not something that is dictated from the theory. Of course, there is a a different expectation than what we have in standard cosmology, because of the presence of this contractive phase, the quantum states arrives to the onset of inflation being already excited, but otherwise the states needs to be chosen. So very much of my research was going in the direction of trying to include in the treatment of cosmology more and more informations from the full theory, and in order to make cosmological predictions. And one of the things that I mentioned to you is the fact that so the states in the usual formulation of quantum cosmology, the states are not the standard states of loop quantum gravity, but in fact, I have been arguing that the states of loop quantum gravity can be used in a very natural manner to describe cosmological states in the following way. So the states in loop quantum gravity are, well, first of all, the theory is defined with different choices of states, so that the first formulation of the theory was done with the so-called loop states, but then later it was realized that using the spin networks, that the spin network states that were introduced by Penrose in the 70s, were a very clever choice, because spin networks are naturally, automatically different various states. So you can think, so spin networks are graph states in which you can picture each node of the graph as being elementary quanta of space-time, and the links represents the interactions between these quanta. I think in this audience there are some mathematicians, so at the more mathematical level, the nodes are SU2 gauge invariant objects. They are the intertwiners, and the links are colored with SU2 representations. So basically these states are defined in terms of representations of SU2. But bear with me, so the basic idea is the fact that these states, you can think indeed them in terms of elementary quanta and how these quanta interact one another, or you can think of them as a sort of cosgrain, as so you can think of them as a representation of a generic geometry in which each of the quanta represents just some generic space-time region. Or so if we wanted to focus on a given time, so if we fix the time, then each state represents an elementary volume of a region that we are describing. So this, how this connects with cosmology? Well, if you think of cosmology as a theory in which we consider an expansion in modes, namely what we are doing when we do cosmology is to describe the largest mode of this expansion that corresponds to the scale factor. So in cosmology, through the symmetry reduction, we consider just 1 degree of freedom. And then with the idea that you can add more and more degrees of freedom. So in fact, we have models in which we add more and more anisotropies or inhomogeneities. But in principle, you can think that you can add an infinite number of degrees of freedom, and then you recover the full GR. And in the same way, here with these graphs, you can start with a very small graph, but the full theory is defined for the limit in which this graph tends to infinity. So you can really associate small graphs with spacetimes that can be described by only few degrees of freedom. And actually, okay, so in cosmology, you have just 1 degree of freedom in a Friedmann-Lemaitre-Robertson-Walker spacetime. If you wanted to add, if you have to associate with the most elementary spin network, 1 degree of freedom would be just one single node without even any links. But as soon as you start adding links and nodes, then you get more degrees of freedom. And in particular, so if you start working, for instance, with a graph like this, that is what I have done recently in the work that I will tell you about later. So if you have a state like this, so you have already many, many degrees of freedom. Or we started at the beginning working with a state like this one with 2 nodes, and the 2 nodes again is already many degrees of freedom more than what is usually considered in standard cosmology. So in this sense, you are already including in the theory some anisotropies and inhomogeneities. So I can recommend, I forgot to put a reference, but for instance, there is a nice review on this by Antonino Marciano and collaborators. So, so one point that I'm trying to make here is that careful, because the theory I'm talking about is a theory in which there is quantum discreteness. So I'm talking about elementary quanta of the gravitational field, but this quanta should not be confused by the fact that I'm using a graph to describe them. And also, so I have to think about the graph truncation as a kind of approximation. And these two things have a non-trivial interplay in the realization of a quantum cosmological model. So what I want to do in this talk is to describe how I have been using with collaborators covariant loop quantum gravity. So I will focus on the covariant formulation of quantum gravity that is referred to as spinfoam. Spinfoam because you can think about the space-time as coming out from a bubbling of these quantum fluctuations. Then I will show you how one can define a Lorentzian spinfoam state, and in particular, I will describe a no-boundary state, the same fashion in which you can have a no-boundary state as was originally described by Hartle and Hawking. So this is quite an older result from 2011, on which I have worked with Carlo Rovelli and Eugenio Bianchi. And I will arrive by the end of the talk to give you the flavor of a more recent calculation that I have done in collaboration with Francesco Gozzini. Actually, he has done the calculation in the sense that we have tried to compute cosmological observables associated with this state using new numerical techniques. So I have to thank Francesco for developing these numerical techniques. And then if I have time, I will discuss a few conceptual aspects. So the first thing to say is that I'm describing, I'm using covariant loop quantum gravity. So the dynamics of the theory is described in terms of transition amplitudes. So I wanted to work with gravity in the same way in which I work for other fields, as I do in quantum field theory. And well, this is a covariant quantum field theory, so there will be a difference. But the point is that the dynamics is really coded in transition amplitudes. But now the transition amplitudes are what? So the transition amplitude is, of course, is the probability to go from one state of the geometry to another. But the the transition amplitude is also what gives me a portion of four-dimensional Lorentzian space-time itself. So the idea is that first of all, the computation is done locally, so I don't have to invoke asymptotic states. What I want to do is just to take a four-dimensional Lorentzian space-time region, and so I fix the region. This region has a boundary. The boundary of this region is my quantum state. So in particular, I can think about this boundary. So I can take the different foliation of this space-time region, and there could be one foliation in particular such that I can factorize my boundary in two parts. So I can really talk about a state, an initial state and the final state. But this is not necessary. I can also, so the important thing is to think about this boundary, and the transition amplitude is what happened in the bulk. And then, if instead of considering a boundary state that is factorized, I consider the boundary states as a whole, then I have what is called the Hartle-Hawking state that is given by this expression here, that was defined, well, the origin of this state was given by the fact that at the time, working in cosmology with only 1 or few degrees of freedom was considered more accessible than trying to do the computation for the full theory. So in this sense, this is really a cosmological state. It's a state on which the integration is an integration over geometries, over, if you want, over the metric, or whatever you pick up to represent your geometry, and then you have the exponential of the action here. And in loop quantum gravity, we have exactly the analog of this state that, well, okay, you don't have to capture the details of this calculation, but the point is that there is an explicit expression for the states. And the nice thing is that this expression has a number of nice properties that I will tell you about. But first,
the integration variable in the state be G and not Q?
Sorry, can you repeat again?
The integration variable be G and not Q.
Now Q is because on the boundary, so G, it would be the generic metric. And since you see here, I'm taking the boundary of some space-time region. So the integration is on what I have on the boundary, the metric that describes the boundary. So that is one dimension less.
But if you're integrating over Q, how can the thing be a function of Q?
Sorry?
If you're integrating over Q, how can you have a function of Q, psi h of Q?
Okay, so okay, let me let me think about this. So in the same way here, so I see your point. What you're saying is that I am integrating over Q, so Q should. So what I'm doing is
the Q should be a G inside the integral.
Well, no, in the sense that I am integrating only on the bound. Oof, wait. Let me think for the moment, because okay, so you may be right in the sense that what I want is to consider a boundary state, and indeed I wanted to integrate over all the four-dimensional geometries that are compatible with this boundary. So yes, you're right that I am integrating over four-dimensional geometries. Okay, thank you, Shelley, for making this point. Yeah, I agree. Okay, and the point is that so the important thing is to have clear this picture that the boundary, the Hartle-Hawking state is a state in which I have a three-dimensional geometry, and I integrate in over all possible four-dimensional geometries that are compatible with this. And exactly in the same way, in the loop quantum gravity computation, I take a state of the geometry that here I can represent with a graph state. And then I can sum over all possible four-dimensional geometries that are also represented by, now not by a graph, but by a spinfoam. And so integrating over all of them, I obtain the correspondent states, the spinfoam states corresponding to the Hartle-Hawking one. And I wanted to make a point here regarding the fact that, so I told you that I can take my boundary states and consider a factorization, or I can think about the boundary, and I can think about the peculiar state of the Hartle-Hawking state in which I consider this in and out altogether. But let me make this point. So now I don't know if this doesn't look good because I'm not using the full screen. Now let's see if we can do it this way. Hopefully, yeah. Okay, I hope it's gonna be.
This is good, I think.
Yeah. So in the classical theory, so let me take the classical theory for a cosmological setting in which I have a cosmological constant, or it would be similar also for the case in which I have some matter field. So this part is what remains of the Einstein-Hilbert action after I consider the symmetry reduction. So I have A, that is the scale factor, and A dot, that is the rate of expansion square. So if now I write this and what I obtain is that this is just the difference between two volumes, an initial and a final volumes. This difference translates into a factorization when I consider, when I insert this action in my transition amplitude. So what happens is that there is a factorization of the transition amplitudes in two parts. This is, of course, something that happens just in the first order in an expansion in H bar here. So in fact, there should be other terms, but nevertheless, if I'm interested only in the dominant terms of this expansion in the dynamics, this is given by these two terms that, so you see, those are functions of my initial initial scale factor and final scale factor. So these two amplitudes, if you want, they can be seen as the probability of the universe to exist in this particular state of the geometry, and times the probability of the universe to exist in this other geometry. So each of these two functions, each of these two amplitudes is one Hartle-Hawking state. So I can just study them individually. And it's very interesting that we got exactly the same factorization when doing the loop quantum gravity computations. So basically, when we compute the transition amplitude, we have an expansion in vertices, in the number of vertices that are inside the spinfoam in the bulk of my four-dimensional region. And so here you can have these two three-dimensional states, and what is in between is the spinfoam that corresponds to my four-dimensional space. In this one vertex approximation, it's factorized between this Hartle-Hawking state and this other Hartle-Hawking state. So I can just study one of these objects and try to do computations, compute cosmological observables with it. Okay. So let me just say a word regarding the amplitudes. Well, I don't want to go, I don't have time to go into the details of this, but the point is that this, in loop quantum gravity, we have a theory that is sufficiently developed to do this kind of calculations, having transition amplitudes that respect a number of nice properties, like having a superposition. So we have superpositions of different geometries. The expression of the amplitude is local in the sense that is the product of different vertex amplitude. It's completely Lorentz covariant in the sense that these amplitudes are really completely Lorentzian. This is an important step with respect to the old calculation by Hartle and Hawking. It's finite, and if you compute the classical limit of it, you get back GR. So they are well-behaving amplitudes with which you can try to look for observables and trying to do concrete computations. Okay, this is just an animation of the way in which it works. You have an initial state of the geometry, and then, for instance, a typical process is a process in which you go from a state with one quanta of space to three quanta of space, very much in the same spirit of what you have in quantum field theory. This slide is a sketch. I wanted just to sketch it to tell you that the theory not only behaves well, but is not a fancy one in the sense that it's Lorentzian, we work in 4 dimensions, and it's simply based on general relativity, using as fundamental variables the tetrads and its conjugate variable, that is the spin connection. And once you do so, you can write the Einstein-Hilbert action now using the tetrads, and you discover that everything is nicer if you add also this new term. So in this way, you write the theory as a BF theory, and a BF theory with constraints. And the BF theory are very easy to quantize, and the quantization of general relativity then amounts just to the quantization of the constraint itself. So you promote these objects that appear in the constraint to operators, and you discover that there is a relation between the operators that describes the area and operators that describe boost. And I was saying, well, I want to say this just for the mathematicians in the audience. There is, it's a beautiful realization of what is called the. So once I do this properly in the quantum theory, using my states, using the full representation theory, this is a beautiful realization of what is known in representation theory as Vaughan K-type of representations. Where in fact the K of the Vaughan K type is this gamma that is called the Barberi-Mirzi parameter that appears here. Okay, so if you have more questions regarding this, I have a nice book suggestion, but I don't want to go to this. I wanted to discuss how this can work in order to do cosmology. Paola, can you tell me how I'm doing with time? How much time do I have?
Yeah, you have about, well, let's say 5 to 10 minutes. Is that fine?
Okay, good. 10 minutes is better,
okay.
but yeah, okay, very good, thank you. So let me tell you the philosophy behind this computation. First of all, so I wanted to describe a quantum state of the geometry that really represents the state of the universe in its full quantum regime. And this provides me with a very interesting situation in which I have a system that is a quantum system. And, you know, in quantum mechanics, in order to conceptualize what we are doing, we need to make a partition between my quantum system and an apparatus, an observer, or some other system that is taken to be classical. So this provides the so-called Heisenberg cut. So in this case, the cut is not in space between two systems, but is actually a cut in time. So the distinction is between the system in the early universe that I am describing and myself now in the current classical universe. And there is a distinction between the degrees of freedom that I'm describing in the early universe, that, as I said, are those, the first ones, the heaviest one in this expansionary modes, that are not the same as my degrees of freedom that are very, very small, that are definitely different than the one that I describe in my quantum state. So the partition that I'm doing is between a state in the past, a state now, is between large degrees of freedom and the degrees of freedom that I am, that are different. I wanted to use the graph approximation. This is something I have already discussed before, how I can choose to work with different graphs to describe different physical situations. In particular, choosing a very small graph is appropriate when I wanted to do cosmology, when I wanted to describe only a few degrees of freedom. Then I wanted to consider a Hartle-Hawking state. So I take a given three-dimensional geometry, and I look for all the four-dimensional geometries that are compatible with this boundary. So I can compute the transition amplitudes in the way in which I sketched before, and so this gives me a way in which I can obtain a quantum state of the geometry. And the interesting thing of using this state is that then I can compute observables that I can interpret as cosmological observables. And in particular, the kind of quantities that I want to study for these states are quantities such as the entropy of these states. But now, so the entropy that I would obtain, or the other properties that I will obtain, they are not the ones, so for a given geometry, the values that I obtain are not the ones that I choose for that given state, but they are really the ones that are dictated by the dynamics of the theory. So what are the kind of observables that I'm interested in? So once I have this spinfoam Hartle-Hawking state, I can compute on it quantities like area, volume. I can compute the dihedral angles that would correspond to curvature. So once I have those quantities for a given graph, so what you can imagine is that in the graph, different nodes corresponds to different space region. So for instance, I can fix the volume of one region, and I can see how the volume of the other region, of some other region would change. So I can look for correlations between different, the properties of different space regions. And this is exactly what we need when we do cosmology, in order to connect our computations to observations, because what we observe in the sky when we look at the CMB are exactly the correlations for different densities at different angles in the sky. So that's the idea, that we can write down states and we can use the dynamics of a quantum gravity theory to see what are the natural properties of these states, including entanglement, including correlations, so that we can translate into cosmological observables. And we have, so what we have obtained so far, myself and Francesco, was first of all to see that the emerging geometry in my Hartle-Hawking state is indeed a three-sphere. So we wanted to model the universe at the classical level as a three-sphere, and we have checked that our quantum states indeed presents the right properties that corresponds to a three-sphere. And this was just a check, a preliminary check, but at the same time it was highly non-trivial, so good for us. But then the most interesting part is that we found that we have large fluctuations. So we have very wild oscillations of the values of the quantities that we are computing, like for instance, as I was saying, like a given volume. And we have an amount of correlations between different space regions that is higher than what one would expect. So, of course, this was a preliminary work in the sense that the kind of graph that we have used was relatively simple, but I think of this work, first of all, as a proof of concept that this kind of computation can be done, and it gives a meaningful framework to do cosmology. And second, well, in every case now things are continuing, our research is continuing, so also with our other students here at Western, we are continuing to, like Pietro Paolo Frisoni, we are continuing to develop the numerical techniques to compute these observables. So the goal is to check if those large correlations that we have seen would persist as we refine our model. If they do, this will be extremely interesting because, as I told you at the beginning, what happens in cosmology is that one has to make a guess about the initial state. And the choice is a choice that is dictated by the fact that one wants a nice state that fits well things with inflation. So, but what if the quantum gravity theory tells you that the states should be different? So what new constraints would this give to inflation? Or can we even get rid of inflation as a whole if we have enough correlations already present without having to develop them using an inflationary theory? So these are the kind of questions that I'm trying to address with this work. And I think this is an interesting framework to ask philosophical questions, more conceptual questions, such as what are the observables? In particular, we are using a theory in which localization is not a localization in space and in time, because we are doing a theory of space and time themselves. So what does it mean to compute observables in this case? What are the well-behaving observables? Well, I believe that I gave you an example, like the area and volumes that I can compute for the quanta in my Hartle-Hawking states, an example of how this can be done in practice. It's already realized in practice. There is a question how we should think about time in this picture. What are the degrees of freedom that we are describing? What is the interplay between the Planck scale and the cosmological scale? And what is the role of quantum fluctuation of space-time? So again, I think for each of these questions, we have tried in this particular framework to give an answer. But these are open questions, and they are also addressing these questions allows us also to check the viability of the model that we are considering. So to summarize, I have, well, I wanted to connect with the next talk by Stefano. So I wanted to state again, no curvature singularities in loop quantum gravity. We have one can take this information and then try to see what are the consequences for cosmology of this. There are already consequences when one does loop quantum cosmology, so using the canonical dynamics of loop quantum gravity, but I think that also using the covariant dynamics of loop quantum gravity, we have to take this into account, implement it, and see what we can say new about cosmology. So I sketched to you a way in which one can compute from scratch a quantum state of the geometry, in which we can compute the quantum fluctuations of the geometry, the very quantum fluctuations from which all the structures that we see in the universe should come out. So we are doing the universe from scratch. This is also a way to address the problem of initial conditions in cosmology. It's also a way to show you that loop quantum gravity allowed to do computations, to compute concrete observables that will correspond to observed quantities. So, and I hope I have given you an idea of how rich this conceptual framework can be. So thank you very much for your attention. And I wanted to conclude with Carl Sagan again.
An apple pie from scratch. You must first invent the universe. Space is filled with a network of wormholes.
Okay, and that was it. I'll try to.
Thank you. So thank you, Francesca, for this interesting talk. So I think there are a couple of questions. So let's have like 10 minutes for the questions before we then start with the second talk. So there was already one question during the talk, which we postponed. So Siddhant, would you ask it? Siddhant?
Sorry. So there was a remark somewhere near this path integral you showed that you can recover general relativity. So I was wondering if you could elaborate on that.
Yes. In 2009, there was a very nice result by John Barrett and collaborations in which he showed that the classical limit of this amplitude was giving back the exponential of the action for GR. Actually, to be more precise, what it was obtained was e to the I a discretized classical action of GR, but nevertheless, so this is a discretization that is similar to what you have in a lattice. The important thing is that the classical limit that you are taking, that if you want, you can think about it as the limit for h bar that goes to 0. It's a bit more complicated because we have also you have to consider the Planck length, but you have also to consider the presence of this new parameter gamma that appears in the theory. Nevertheless, so if you take this limit, you get back a discretized action of general relativity. The way in which it's done technically is very similar of what happens in standard quantum mechanics, in which we have observables that are written in terms of quantum numbers, and so that are functions, of quantum numbers, and so when you have a Dirac bracket of observables and you take the limit for very large quantum numbers, you have as a limit the corresponding Poisson bracket of the Poisson bracket of the corresponding classical quantities. So this is exactly, it's basically the same thing. It's happening the same thing.
Okay, thank you. Then we have another question here by Sahan Tokasi. Sahan, do you want to ask?
Yeah, thanks for the talk. I wanted to ask, well, at the end, I mean, if you start with this approach, what one would like to get is that, for example, for some hydrogen atom or helium atom, you would be able to derive the discretization of energies, the states having different energies, the typical quantum things we see. And my question is, how far is your approach to this point, so that you can derive the quantum phenomena of matter from your approach? And if it is very,
Sorry. Yeah, sorry. Careful, I'm not talking about matter. So we have already a beautiful, wonderful quantum treatment of matter, thanks to the standard model. There are extensions of the standard model. Personally, for instance, I like a lot the approach of no-commutative geometry. But what I'm doing here is to consider the quantization of the gravitational field. But you are totally right that what I want to do is to have a theory that gives me exactly the same thing as the angular momentum, say, in quantum mechanics. So in the case of the quantization of the angular momentum, I have a minimal angular momentum, and then I have discrete values for it. And this is exactly the starting point of loop quantum gravity that was obtained by Smolin and Rovelli back in 92, in which, so when they computed the discretization of the area and the volume operators. So thanks to the fact that you can write a general relativity as a gauge theory, and in particular, so well, the gauge group is supposed to be the Lorentz group, but inside the Lorentz group you have the rotations. And when you consider states at a given time, only the rotations matter. So indeed, the mathematics is exactly the same as the one that you know for the angular momentum, in which there is also a SU2 symmetry. So the computation is quite straightforward when you compute, for instance, the eigenvalues of the area, because they are SU2 eigenvalues, and you get exactly the same structure as the one that you know for the angular momentum. But this is all the results. Now we are trying to implement this information that we think it's solid into cosmology. So once you know that there is a minimal area at the Planck sites, that there is a minimal volume, what consequences you have for cosmology?
Okay, thank you.
Okay, so we have another question by Ayman Al-Iriani. So you can ask yourself, please. No? But I think you are not muted anymore, so you could ask at least.
Hello. So can you hear me?
Not very well, but yes.
Okay, so I can go on with the question, or try to. So concerning the discretization of area, I was curious, I mean, since the analogy with angular momentum is such that one has a minimal area, then doesn't this mean that the more, so the more lattice points one starts with, then the minimal area would be larger. And then if you choose an infinite number of lattice points, or a very big number, then the minimum area would also get larger and larger. Something.
Yeah, that's one. So the idea is that you can consider your quanta of space-time as having a minimal area or a minimal volume. Maybe let's think about three-dimensional space-time. You can have element each of quanta that is in its state of minimal area or minimal volume, sorry, and then you can construct a very large space-time putting together lots of them. This is a possibility. This is not the possibility that I was, I saw among the participants Daniele Oriti. Daniele Oriti is an expert of doing these kind of things. What I was doing here was taking a different road, namely saying this is not necessary. You can also do something else. And so you don't have to describe each single quanta being in its minimal state, but I can also imagine to describe a large space-time region by doing a sort of cosgrain as being represented by a single effective quanta, if you want. That is the logic behind what I was presenting. But of course, the other possibility of having many quanta is interesting, explored, and I refer you to the experts of that.
And so in a sense, if we're just talking about a small volume of space-time, so we want to just discretize a small volume of space-time, then we have we cannot take, there is a maximum number of vertices or a maximum number of nodes that we can choose.
Yes.
Is that correct?
Yes. If you have a finite space, there is a maximum number of quanta that can fill it. You can also describe it only with one quanta if you want in an effective way. But on the other hand, there is also a maximal amount of quanta that can do the job.
Okay, maybe I would stretch the question, but and what determines this maximum number of quanta?
Sorry?
What determines the maximum number of quanta?
Well, I can give you a rough estimation in the sense that, I mean, if you, the rough estimation would be take the volume of the universe and divide by the minimal volume that it's proportional to a Planck volume, and you get an estimation of the maximal amount of quanta you can have to describe your universe. But well, actually, I think that this is a very rough estimation, and in describing a quantum state, such a macroscopic quantum state, there could be other effects, and so like concerning the interactions between the quanta. So I cannot really think if maybe there is some other effects going on here, but yeah, that would be
Okay.
a first approximation you can do. Just you know, throw in numbers like physicists do.
Okay, thank you.
Maybe can I ask a follow-up question to that? So you have the number of quanta, or this, so this corresponds to the number of nodes you have in the graph.
Yes.
And what about the number of connections between the nodes? How do you figure out how many?
Well, the way in which you choose the graph depends on, first, try to start with a simple graph, not very one. So, you want to add nodes and links.
Yes.
Depending on the physical situations that the physical system you want to describe. For instance, something that I didn't want to go through in my talk, but maybe it's worth it to mention here, is that the graph that I'm using is dual to a triangulation of some space-time. So you can think like some polyhedra, like a tetrahedra, and you put a node in the center of it, and then you take another polyhedra, say another tetrahedra, and you put another node in the center of it. And then if you wanted to glue them, they would share a face. And if they share a face, it means that they are in interaction. And I would represent this interaction as having a link between them in my graph.
Okay.
And now the representations that stay on this link corresponds to the area of the shared area between these two polyhedra, so between these two elements of space-time. So the point I was making is that when you consider the description, when you wanted to describe a given space-time region, you may want to start with a given discretization of it. That could be, for instance, if I wanted to do a homogeneous and isotropic cosmology, I may want to have a regular discretization. And so this already kills a lot of possibilities because, for instance, so even in the case of three spheres, there are only limited regular triangulations. And then you can construct the graph that is dual to this triangulation. Well, the richness of the theory is also in the fact that working with these abstract graphs, you can describe also geometries that are not very easy to visualize, and they don't have a direct correspondent in terms of some standard geometry, standard Lorentzian geometry.
Thank you.
You can have very degenerate configurations, and these configurations can also contribute in the quantum theory, for instance, so they can be present in the transition amplitudes.
Mm-hmm. So yeah, let's take one final question, and then we go over to the next talk. Sahant, you can ask another question.
Okay, maybe it's a very general question. If you think it's better for later, I can postpone it. But I ask the question very fast. I mean, how do you feel generally to starting with a universal wave function, which is in superposition of expansion and contraction? How do you feel about? I mean, how do you understand such a universe? I just wanted to see how you get along. How do you get a good feeling about such a state?
I love that particular case because this is exactly what happens in when you have the tunneling from a contracting universe to an expanding one. And so such a state that is in a superposition of two different geometries is indeed exactly what I expected to happen, to be present at what we call the bounce. So
what's the bounce?
The bounce, so in the very naive picture that you can have about what's going on in the early universe is that the universe went through a contraction, a moment of maximal density, and then an expansion. That is what we observe today, is the universe in which we live today. So there is you can think, so the contraction and the expansions are both classical solution of the Einstein equation that are classically disconnected, but they can be in a superposition in a certain era of the universe, such as the one that we call the bounce, the point that connects contraction and expansion. A bounce is like a ball. When you take a ball, you throw it and bounces back. So in this case, we have a universe that contracts and bounces back.
Okay, thank you.
Okay, thank you again, Francesca. Then I think, yeah, that's it for now. And we will now start with the second talk of today. And so I'm happy to announce our second speaker, Stefano Liberati. He's a professor at CISA in Trieste in Italy. And he's well known for his work in gravitational theory, so in particular on black holes, classical and quantum aspects of it. And today he will talk about, well, the title of his talk is Hearts of Darkness, Probing of Black Holes Inside Out. So thank you, I'm happy to see that.
Thank you. Can you hear me fine?
Yes.
Great. So thanks, first of all, for coming and for listening to me. Thanks for the invitation. Okay, so today I want to carry on an exploration with you, which will start basically from a kind of agnostic approach about quantum gravity, but conjecturing what quantum gravity may do inside black holes, and then asking ourselves if these effects of quantum gravity can somehow be visible or observable in astrophysics. So it's a long journey. The long journey starts basically with understanding why we want to go beyond general relativity. So I think that it's always worth mentioning that GR is a theory that for everyday life is fantastic. We use it every day in our GPS system when we look for a place on our mobile phone. It is very effective in describing reality as we experience it. Nonetheless, general relativity is a very special theory. I would say it's a very tantalizing one, because it has a series of properties which are very peculiar. It predicts singularities, with which we will focus later on. And you have a little series of problems. For example, general relativity allows solutions which allow for faster than light travel and time travel solution. It has strange property like gravity fluid duality, like the holographic behavior. And nowadays, of course, we can explain with general relativity the content of our universe, but let me say, it is basically how people sometimes say is the pizza nobody asked for, in the sense that you need a very strange content for the universe to explain what we observe with general relativity. Now, I will focus today on black holes. And why on black holes? Because most of the stuff that you see in the list on the left is basically problems which appeared and were found thanks to black hole physics. So black holes are, in a sense, very special object from the point of view of general relativity. Now, I know that most of you basically know very well what is a black hole, but let me try to introduce in a very smooth way a kind of toolkit that it will be necessary to understand what I will do later on. So from the point of view of describing a black hole, if you need to explain a black hole to someone which is not in physics, a very nice analogy that you can use is the one of a fluid. By the way, it's an analogy that goes through the equation. It's a mathematical analogy. It's basically what I'm going to say is the base of analog gravity, which is a program of research that has allowed to simulate in a laboratory stuff like Hawking radiation in acoustic black holes and to observe it very recently. So let me just stop for a moment on acoustic black hole. So this is, you see on the left, is at the Monticello Dam in Napa County in California. This is a kind of sinkhole, gigantic sinkhole, like the one you can have in your kitchen as well. Now, if the velocity with which the fluid flows becomes supersonic at some point, if you look here in a simple sketch where you have a space and time, you can talk about sound cones, basically the propagation of sound in your system. And you see, if you are in a supersonic regime, the sound cone will look like this on the left. But if your flow is becoming sonic and then supersonic, what is happening is that here is the flow is coming from left to right. What is happening is that even the branch of your sound cone that was pointing inward in this case, or outward in this case, with respect to the flow, is tilted in the opposite direction. But this is obvious why, no? Because basically it's like you can see in this picture, what is happening is that the sound waves are dragged, they propagate at the speed of sound outward, but even the ones propagating outward are not able to escape a supersonic flow. So this is what is called a mute hole, or sometimes it was used by Biluru Dumble, but then was corrected because it wasn't politically correct. What it is really a black hole then? If here we suppress a dimension, actually in this case, we don't need even to suppress a dimension. So if you have time here and radius here in a certain sense, this is the situation where if you have an area here, then after some time, the causally connected area through your causal structure, which is determined by the sound cone, will be a larger area. But if you are in a region where the flow becomes supersonic, you have this kind of tilted sound cones, and the area which is connected, which can be reached by the information on the original area after some time, it will be smaller. This is the concept of a trapped region, of a region where you cannot escape, even traveling at the speed of propagation of your signal. In this case, the speed of sound. Now, mutatis mutandis, you can do the same thing in space-time. If you have a space-time, you can think of it where the fluid flow replaced by space-time curvature and the sound cone by light cones. And what is happening is that if you flow into a black hole, you see your light cone, even the outgoing rays, are now tilted so much that they cannot escape. Now, this is basically providing for us a toolkit that we will use in a second. But let's say that the black holes originally were not easily accepted in general relativity. Even Einstein was very skeptical about them. And only later on it was realized that they are really prediction of general relativity and physical prediction. Nowadays, we observe objects which have all the properties that we associated to the exterior spacetime to a black hole of different sizes. Just to make a comparison, this is the largest black hole we have observed so far, is 40 billion solar masses. This tiny spot here is our solar system. So they are monsters that are populating our universe. And now we indirectly see through the observation of gravitational waves. So definitely there are objects in the sky which are like black hole of general relativity. However, if you accept that there are black holes, you have to accept the whole package. And the whole package of black hole is that black hole inside have basically the end of space-time. They have singularities. And not only they have singularity, but in the case, for example, of rotating black hole, they also have what we call Cauchy horizons. What is a Cauchy horizon? It's basically a region, is a boundary of a region beyond which you cannot evolve your initial data problem. So normally in physics, we set up a problem with initial data and we evolve it in a Cauchy problem. Now, in black holes, not only you sooner or later meet the singularity inside a black hole, but even worse, before you meet the singularity on scale which are much larger than the Planck scale, you have this Cauchy horizon. You are not able to propagate your data and you solve your Cauchy problem. You have an end of predictability of space-time. So these features are very unpleasant for physicists, basically because they're telling you that you cannot do the physicist's job, which is to predict the outcome of equation. We lose predictability. So normally what is the standard answer is that quantum gravity has to solve this. Quantum gravity has somehow to allow you to have a full resolution of this sort of problem and predict what is going to happen inside the black hole once the horizon is formed, the trapping horizon that we talk about, that is the boundary basically of the trapped region I described before. Then somehow quantum gravity should be able to deal with these unpleasant features of black hole. Now, a cautionary note, for those of you that have been in this series of seminars, you may have heard that the seminar by Sir Roger Penrose that is making a point that it's not so clear that quantum gravity per se, and here, of course, we have to agree on what we mean by quantum gravity, because there are many different people still now in physics would tell you different answer. But basically, quantum gravity per se may not be able to resolve in the same way all the singularities, or we might need some kind of time asymmetry because the Big Bang singularity and the Big Bang singularity inside black hole may look different. Well, to go even backward, in 1995, there was a paper by Horowitz and Myers claiming that quantum gravity should not resolve all the singularities. For example, if you want, you may have problem if it does so, because you may build in that case a negative mass Schwarzschild solution. Schwarzschild solution is the solution describing the exterior of a spherically symmetric object in general relativity, which is basically also the exterior of a non-rotating black hole. And the negative mass one will have a time-like singularity, which is a singularity which is corresponding to a surface which is orthogonal to space rather than on a space surface, like in the case of singularity in Schwarzschild or in the Big Bang. And these singularity are always associated with Cauchy horizon again, and with lack of predictability. So they say, you don't want to cure the singularity because this way you can say that this space-time are unphysical. You want to cure the singularity in Schwarzschild, you don't want to cure this one. But of course, nowadays, we don't think anymore that quantum gravity is just a quantization of the gravitational field in the quantum field theory sense. Most of the proposal nowadays entail some sort of discretization. Then you have to describe the classical or continuum limit. So in a certain sense, you would cure completely this issue, and even the issue of time machine, for example, if you demand that your quantum gravity theory generically can predict in the classical and continuum limit only global hyperbolic spacetime which is a fancy way to say spacetime which are everywhere predictable, which do not have Cauchy horizon. So this is an interesting provocative question. Can quantum gravity generically, can we say what are the properties that a quantum gravity theory should have in order to univocally produce global hyperbolic spacetime and not allow transition to non-global hyperbolic spacetime? So anyway, I will take here a very humble approach. I would say, I don't know anything about quantum gravity. I just want quantum gravity to deal with the nasty stuff that is behind the horizon of black hole. Because in principle, if you fall into a black hole, you will not able to tell anybody, which is sad, you will die at the end. Probably if it's large enough, you will die after seeing what there is inside the black hole. So that could be a very nice way of dying. But if it is small, instead that you not even cross the horizon, you will be spaghettified. That is a really very miserable way of dying by a black hole because you will not see what there is inside black hole. So who cares? But anyway, so coming back to not dying, but trying to do physics, the point is, okay, we will take an humble approach. So we will say, okay, I want just to assume that my spacetime is such that is quantum gravity, whatever is quantum gravity, including maybe modification of quantum mechanics, I don't know, cure the interior of black hole. So what then can happen? Can you do that and having effects which are not long range? Can you cure the singularity inside, having a completely regular spacetime, completely predictable, and nothing can be said outside of these objects? So let's see. Let me see. Okay, let's go back. Why we are so sure that there are singularities inside black hole? Well, this is basically the Nobel Prize for Physics. I would say is part of the many contributions that Peros has given to physics and mathematics. But this one I think is really fundamental, which is the Peros singularity theorem. So there are several singularity theorems also applied to cosmology, made also by Hawking, Ellis. I'm really referring to the original Peros theorem, which is a masterwork. It's a 3 pages PRL, which is I think the paper everybody in this field would like to write sooner or later. And the theorem is basically simple. Say, okay, assume that you have GR. Assume that the gravitational collapse becomes enough strong to have a trapped region, exactly in the sense I told you, that the light comes bent so much that basically even the outgoing light rays are starting to converge inwards. Then, if matter gravitates the standard way, that means it's not exotic matter, doesn't violate some condition on their energy, which are called energy condition in general relativity, which we don't need to dwell with, then the conclusion is that here there will be a focusing point, and this focusing point for the outgoing, there would be outgoing rays that are dragged inside nonetheless. Here, this point would be singular, cannot be part of your space-time. And the demonstration goes in 2 steps. But before you show that there is this focusing point, with an equation for those of you that are more into GR, that is called the Raychaudhuri equation, and use the energy condition to predict the behavior. Basically, that gravities will suck inside, will tilt these light cones in a situation like a stellar collapse. And then the second part is purely topology. It's a topological theorem, so it's very general. Now, in order to avoid the deformation of a singularity, like we are hoping that quantum gravity will do, basically you have 4 options. One is that this condition on the positivity of the energy of the matter is violated at some point, that the equation of Einstein do not hold at some point, or that you miss really the Lorentzian geometry, the idea that there is a continuous pseudo-Riemannian manifold. Pseudo-Riemannian is a fancy way to say that there is a time and space and not all space. It's not Euclidean, okay? So the idea is that somehow you have a place where geometry is not defined. And then you want also, another things that may fail is global hyperbolicity. That means again that there is somewhere your Cauchy problem cannot be evolved anymore. What I'm going to do now as an exercise is that let's conjecture that quantum gravity maybe as a region, as a transient moment in which you don't have a well-defined spacetime, but the outcome of what it is, this regularization by quantum gravity, is a space-time where you have everywhere a well-defined Lorentzian geometry, and everywhere is predictable. So we are going to give up or to renounce to the energy condition of matter, also because we know that quantum effects generically violates all the energy condition. For example, Hawking radiation violates the energy condition. The Casimir effect violates the energy condition. And also we know that in principle, extra degrees of freedom with respect to the two of gravity can switch on in a very high regime. And so maybe the Einstein equation cannot hold. Maybe you can still have an effective field theory for gravity that looks like a modified theory of gravity, but will have extra term with respect to the Einstein one. So let's assume this, that we neglect that quantum gravity violates the two condition and preserve the last two. Now, what I was telling you about the trapped region is again the picture that you have here. So I will K basically the ingoing light rays, and L the one that are normally outgoing. And this is a case in which you are not in a trapped region, because the area that is connected after some time is larger than the one you started with. There is an object which is called expansion, which describes exactly this, that the area grows or shrinks. If the expansion is positive, it means that if you have along these null rays, you have it's like, imagine a beam, it is expanding isotropically, then the expansion is positive, and this is the case here. But if it's is converging, the expansion will be negative. Now, in Perrot's theorem, you have basically this focusing point. So the idea is now, can I avoid this focusing point? How can I avoid it? You can avoid it basically in few ways. This is the interesting part about this study, now that you don't have many possible outcomes, or much less than you may wonder you may have without having the full dynamics of quantum gravity. So one possibility is that you defocus these rays that we're going to do the focusing point, and then the second part of the Perrot's theorem is telling you is a singular one, is a missing one, more properly. They will defocus at a fine distance along the ray. So you have a parameter, it's like a time along the ray, but these are light rays. So instead of a proper time, you will have some what is called an affine parameter. But at a finite value, you will defocus, so you escape. Or you do it at infinity, you never converge, they never focus, or you have a defocusing but only pushed at infinity, or they focus but at infinity. So if you have focusing at infinity, you still can show that you see there will be a focusing for the ingoing congruence, and that will correspond to a place where the curvature diverge. So I'm asking, when I say that spacetime is regular, I'm implicitly asking two things. One is that geodesics are never truncated, that they can prolong up to infinity. And secondly, that the curvature doesn't blow up nowhere. Basically, I'm telling you that the first derivative of the metric and the second derivative of the metric are both regular and continuous. Now, if you have a focusing point at infinity, still you have that for this going congruence, you have a blowing, they will see the curvature blowing at some finite distance. So for us, it's not a good case now under our assumption. So then you have 4 possibilities. So just to tell you one, you have the focusing at a finite parameter. This R0 is the radius corresponding to the defocusing, how big is the radius at which you defocus. And then you can catalog the cases depending on the behavior of the expansion of this other object, this other congruence. Normally is negative, and then you have negative, but it can reverse sign also this one, not just this one. The one for L, in order to have a trapped region where you form an horizon, must be negative initially. So we're saying the focusing, it means that it's not converging inward anymore, but it's the focus. But also this one can change sign. And then you can have that the focusing can happen at infinity, so the case 2, infinite affine distance. And then you have, of course, that the other one, the ingoing one, can be still focusing or defocusing as well. So you have these 4 cases. Let's see what they correspond to. But before we do that, I need to introduce another little tool, which is how to draw an infinite space-time in a finite diagram. This is another contribution by Perrot and by Carter. These are called sometimes Carter-Perrot diagram of conformal diagram. you see, you have in general relativity many ways to go to infinity. There is a space infinity, a time infinity, but then you have infinity also for light rays, which are traveling at 45 degrees in this diagram. So you have future light infinity, in jargon is called null infinity, past null infinity, and another one on this slide. So Minkowski, if you bring this infinity with a transformation on your metric, which is called a conformal transformation, is a rescaling of length to bring infinite distance to finite sizes. Basically, you have an object like this. This is Minkowski space in a Carter-Perros diagram. So you see light like infinity, time like infinity, space like infinity. Now imagine you have a star sitting here. This is a line of constant radius in this Carter-Perros diagram. If you could have that the line form, the star collapses and form a black hole, basically you have a truncation of this diagram. You see it's missing a part. Here I'm not drawing the other wedge of this Minkowski space because it's basically not containing any additional information. You will have, oh, sorry, another ray, I don't know. You will have another, the surface of the star will appear also here. So imagine now we look at the star collapsing. You have a deformation of a singularity that cuts out your space-time, and then you have the horizon, the event horizon. And the notion of an event horizon, you see, now you have null rays that are traveling this way, and only null rays that are doing this. They are traveling through the center of the star. Instead of drawing them this direction, I just bounce them through the center of the star, and then they reach the light like infinity. You see, the difference when you have a black hole is that there are some of them that fall inside and hit the singularity and never reach the null light like infinity. The boundary of the region between the light rays that can reach light like infinity and the singularity is the event horizon. So you see, the event horizon, differently from the trapping region I described you, is a teleological concept. You need to know the infinite future of your space-time to know where the event horizon is. So it's not that useful when you want to do astrophysics, for example. But let me try to draw, and using the same diagram that I just introduced, to describe what are the situations. So the first situation was when you have a defocusing at some point of the outgoing congruence. Basically, there would be outgoing light rays, the one that normally are used in the Perros theorem to say that they focus and you have a singularity there. We say that they focus at a finite distance. And then we have the case in which instead the ingoing one do not change sign. This is the case in which you have a region which is trapped, and basically you have an inner horizon. Basically what is happening, you see, you have a region where light rays are trapped, but only for a finite time and in a finite space. And everything in the end reach light like infinity. So this is like a portion of Minkowski with a very strong gravity region where for a finite amount of time and in a finite region, light rays are momentarily trapped, but then they manage to escape. This is what we call an evanescent black hole, an evanescent horizon, or a regular black hole. Regular because there is no singularity, but there is a trapped region that can be long-lasting. We will come to that in a second. Of course, nothing forbids to have a multiple region. Once a trapped region is disappeared, you can have by symmetry, if you ask, for example, for a time symmetric situation, an entrapped region here, and then you have what it is, to use exactly Francesca language, a bounce. So you will have that matter here collapses, arrive in this region, remains trapped for a while, and then get tunnels basically to this other untrapped region, and then escape to infinity. So here you have basically a collapse. You form an ultra dense ball behind the trapping horizon, which is not an event horizon, because the event horizon, have you seen, it was defined by the presence of the singularity. And then it explodes again. And then you have an anti-trapped region. And this is basically what one could call the bounce in a black hole space-time. Then you can have instead another situation where also the sign of the expansion of the ingoing light rays also change. So also basically the focus, they do not converge to a point, also the ingoing light rays. And that is corresponding to have what we call a wormhole. So this is a very funny situation. This would be you try to form the black hole, but when basically your ball of matter reach probably Planckian density, you have a transition by which you change the topology of space-time and you open a wormhole throat. And this wormhole throat is seen by the fact that you see this is a radius. The radius is decreasing by line of this sort. You have a minimum radius, which is different from 0. And then you, from up here, you start to expand again. So you have you look like everything is compressing. You are squeezed to a very short radius, but at some point everything will expand again, and you have a minimal radius inside your horizon. This is an eternal black hole, so you have also an event horizon here in a certain sense, because there is only a region that where the light rays can reach Scri plus. This region from here they cannot reach it. They go in this other portion of another universe. And then, of course, you have a situation where this is happening, but at infinity. So this is like an evanescent black hole, but lasting forever. And this is like a wormhole throat, but the wormhole that is focusing, the throat is placed at infinity. You never really, you reach it in an infinite amount of time. These are not, I mean, cannot be excluded by this local analysis, but they are less interesting cases, I would say. Now, in order, this is a purely geometrical analysis. Now you may ask, okay, but are this resolution of the singularity viable? Can we really have large-scale structure that are implementing this way of escaping a singularity? Now, normally what you do, you have to see if they are stable under perturbation, if they may describe the endpoint of a gravitational collapse, and then you have to take into account semi-classical physics, in particular, in the case of black hole, if they are compatible with Hawking radiation, for example. So for evanescent black hole, let's say if you have regular black hole, there is a bad news from the start. You see, this evanescent black hole, they have an outer horizon and they have an inner horizon. Basically, they have an interior horizon in order to close the trapped region at a finite radius. Now, if you look at perturbation around this inner horizon, you know that this perturbation, they grow exponentially fast. And this is called mass inflation. It's a generic phenomenon. It doesn't depend so much on the peculiarity of the geometry that you're using to implement the idea of the regular black hole. And that tells you that they are generically not long-living structured. If you don't fine-tune the parameters in your theory, they basically have this instability within a time scale, which is ordered basically of the Planck scale. Is a very fast one, or if you like, in the best scenario, is the light crossing time of the object, how big it is. But the light crossing time is always very small. Now, in the case instead of bounces, the situation is different, because there the question is how long it takes for the bounce to happen. Well, there it's model dependent, the answer. You can take something of the order of the light crossing time, then it would be very fast, and then it would be not easily compatible with the long-living black hole-like object we see in the sky. It can go like the square of the mass, then it would be something interesting also phenomenologically, or it can go like the mass cube, but then it's a very long time, and it's comparable to the time it takes the black hole to evaporate. But then it could be a scenario where at the end of evaporation, where you have a Planck scale remnant, basically you have a bounce and the resolution of these remnants into a bounce. We will go more into this later. When you have wormholes, wormholes are not in the normal sense of the word, because they're inside an horizon, so they are hidden wormholes. You can have two problems. If you have a situation like this, basically you have to change the topology of space-time, and that is very dangerous. It's generically very dangerous. Or you have a local minimum, then you have a situation like this, where the matter collapses in this region. Basically what happens if it crosses this critical radius, from there on, it sees larger radii. So it expands again. But then you need that your metric to not be analytical in at least 2 points. One, because you don't want to arrive all the way to spatial infinity, otherwise your black hole will be infinitely large. And one, because you need basically another non-analytical point. So minimal renunciation to the regularity of space-time can do the job nonetheless. So it may be that some geometry are allowed if you have point-like deviation from regularity. For what regards instead asymptotic everlasting horizon, you have a problem with Hawking radiation. Hawking radiation will not like them because it tends to make the black hole evaporate. You have to kill Hawking radiation somehow. And the same happens if you have a wormhole lasting, which is produced asymptotic. So to make a variability summary very fast, is basically you have that, you see, with the simple analysis, you already have reduced a lot the possibility of regularization of your singularity. And basically what is the most promising one appears to be or the regular black hole or the bounce. Now, can we test this? Can we really test this? So now I've done just a comment about the local behavior of these objects, right? But are there global geometry that are endowing this behavior? So let me throw, regular black holes are something that actually is in the literature, has been for many years now, and where advanced has possibility to exactly regularize, to have a regular solution, which do not entail singularities. As I told you, generically, they have this problem that nearby this inner horizon, they have instabilities. They have a very fast instability. Recently was claimed that it could go polynomial in time, but actually it always goes exponentially. So if you want to have this kind of regular black hole, you need to fine tune in such a way to the parameter in such a way that this instability is longer than expected. But this, maybe that quantum gravity does the job for you, because what is a fine tuning from the point of view of the low energy effectivity theory, maybe it's not, it's something constrictory from the point of view of quantum gravity. Bouncing geometries are very interesting for several reasons. One is the timescale I already told you about, because if the timescale is sufficiently fast, if it is fast that goes like the mass, it's the light crossing time, then what you can have multiple bounces if it is not symmetric in time. And then you can stabilize on an ultra compact object, which is supported basically by quantum effect. There are tentative calculations in this direction. So it would be a quantum, a star, an ultra compact star generated by multiple bounces due to quantum gravity behavior. If instead it goes like m squared, then if the bounce opens the black hole in a finite amount of time, it could be visible as a signal in astrophysics. So the other point is that in order to have a bounce, generically, you have that the geometry outside of the horizon cannot be everywhere a solution of general relativity. So you can have tail effect. You can have that the geometry is not exactly the one of a general relativity black hole. And this could generate a phenomenology that we may see in present and future observation. I told you about the possibility to have an ultra compact object. This is another class of object. Normally, I call them quasi-black holes because these are objects which are very close to form an horizon, but are supported by quantum physics and may be generated only via some kind of quantum gravity tunneling. Now, these objects have a very nice property. You can show that they have basically an O'Hare theorem, that even if they don't have an horizon, for example, if you take a spherical symmetric one and you deform it from spherical symmetry, you see that you have to pay this deformation with a huge curvature. And this huge curvature means that it is strongly disfavored. So this object will tend to be exactly spherically symmetric as a black hole would be. So the more they are compact, the more they behave like black holes. And then finally, I told you about wormholes inside the horizon. You can have also wormholes at black hole mimickers, which are not hidden by horizons. And this is a class of black hole mimickers that have been considered in several studies recently. Now, how you can, well, this is just a comment regarding the fact that then you can have a mixture. This is a recent class of solution, which are pretty interesting. You see, this is like a Schwarzschild geometry, where you replace R with the square root of R squared plus L squared, where L squared is some regularization scale. And this is enough to create a geometry which is regular, that you can generalize to the kerr, to a regularized kerr. And this would be, depending on the size of L, a wormhole inside the horizon or a naked wormhole. So if L is larger than the horizon, you would have basically a naked wormhole. You can have a wormhole with the throat, which is considered with the horizon, or you can have a wormhole with a throat inside the horizon. But this geometry is different from a GR geometry, even outside of the horizon, So generically, this regularization scale can modify the phenomenology. For example, superradiance, and superradiance can modify the bosonic clouds that are expected to form if you have ultralight bosons, like some candidate of dark matter around black holes. So it's just to say that sometimes you have geometry which are meta geometry that, depending on a parameter, can make one of the configuration at will that we discussed before. Now, when you don't know exactly what to play with, what do? You parameterize the uncertainties. So here, for example, we propose to parameterize basically the deviation from how the radius is larger than the Schwarzschild radius. And you have a compactness parameter you can define, which is basically this difference with respect to the Schwarzschild radius if the object is really close to form an horizon. Then you have, for example, the lifetime of the object, the time they take to form, the compactness, as I say, the absorption coefficient, how much they absorb light, how much is the elastic reflection coefficient, and then there will be an elastic reflection, but that is just is dependent on the other two I just gave. And then details, is the metric equal to the one of GR, of the GR black hole outside of the horizon? And then for all of them, you can basically say, what is the expectation? Now you can say, what is the observation that we can use? So let's go to observation, and then I will close. Basically, one way is to start to look at the orbits of star around black hole. We can do this with Sagittarius A star, the black hole at the center of our galaxy, which is a 4 million solar masses black hole at a distance of 8 kiloparsec. And we are very able to see this Keplerian orbit. It's fantastic to see the Keplerian orbit so well. Unfortunately, you can get only a very loose bound on how much the object can be compact, of order 1000. Of course, you can have a mattering falling on the would-be object of the black hole mimicker or the black hole candidate, let's call it this way. And you may say, if it has a surface, some of this will be radiated back to space-time. So we can look for this back radiation from the surface that is would be replacing the horizon, for example, in the case of a quasi-black hole. And then we should be able to put a constraint. Years ago, it was claimed that this excludes the possibility that, for example, Sagittarius A star has a surface. Unfortunately, in that calculation, they didn't take into account that a very compact object, the angle at which light can escape from the sources close up as the object becomes closer and closer to a black hole. So you see, the angle of escaping goes like the compactness, which goes to 0 in the limit of the black hole. So then you can say, what kind of events can create this flux, this backward flux? Well, you can have cataclysmic events like star falling on the black hole, but then you have complicated physics. You don't get very nice constraints. Or you have a steady accretion, like in Sagittarius A stars you can have, and then you have some assumption about the steady accretion. The problem, what it is that if you take into account that only a very minimum amount of light can escape from an ultra-compact object, you get very loose bound. Okay, you can get, if there is no reflection and no absorption, a very strong bounds. You see, this is the deviation from the Schwarzschild radius from Sagittarius A star is constrained to be 10 to the minus 17. The Planck scale would be 10 to the minus 91. So you're far from the Planck scale. It's like a constraint of 100 meters from the horizon, from the would-be horizon on an object which is 10 to the 10 meters. It's pretty good, but not interesting for quantum gravity motivated objects. However, if you complicate things, if you put absorption and reflection, then basically you don't get anymore a very strong constraint. Not only, but if the object rotates, you can even produce that the escaping of light is very much suppressed by the poles and is enhanced at the equator. For example, in the image of the black hole that we have, M87, you have seen probably the black hole shadow by the Event Horizon Telescope. We are looking at a black hole at 70 degrees declination. So basically, we are looking at the bottom of the hole. So in principle, this is an effect that if the black hole is very rapidly rotating, like probably M87 is, then you have to worry that there is even less light escaping from the surface. Other channels, of course, could be the shadow I just told you about, but you see the shadow that we see is basically delimited from the last photon unstable orbit, which is 3M, for example, is Schwarzschild. It's not 2M, where the horizon of Schwarzschild would be. So actually, the Event Horizon Telescope, it would be more appropriately the light ring telescope. So it can do nonetheless things. And if you have long tails, modification of the geometry outside of the horizon, then it may be very, very capable of, with better resolution in the future, to maybe to cast some constraints on this. Then, of course, if you have bounces, then I was telling you that you can have basically emission of light due to the bounce. If the bounce, for example, has a time scale which goes like the mass square of the black hole, of the Wood black hole candidate, then, for example, this is a work of, moreover, that Francesca did some years ago, that where in this case you can have that there is a typically UV component and infrared component. UV component is associated basically to there is a matter which has the temperature of the universe at the time of the collapse. And the infrared component would be basically related to the signal associated with the size of the bouncing object. So in principle, there are channels that one can explore. It's not completely hopeless to see these effects. Then there are gravitational waves. You know, gravitational waves, basically, you can look at the merging of a compact object, and the spiral can, for example, the spiral phase can cast a coefficient on the how these objects are deformable, how differently are in deformation from a standard black hole. But in general, you really need to have the equation, at least of the effective field theory that's beyond GR, that is taking into account the lowest order correction due to quantum gravity in order to do this. It's not hopeless, but it's complicated. You have basically to suppose a model. Then recently, there has been a big clamor with echoes, you know, because if you have something like a quasi-black hole or a wormhole, what you have is that there is a typical gravitational potential around black hole, which is as a barrier here, and here there would be the horizon on the left, far on the left. So when you have gravitational waves, normally a part is transmitted beyond this barrier, and a part is reflected, but a part reflected plunging to the horizon and is lost forever. If you have a wormhole which is symmetric and you have a throat which is traversable, you will have another barrier on the other side. So what is reflected at this barrier bounces on this barrier and then goes back. And if you have a quasi black hole, that is the same. You will have basically the wave that is reflected here bounces here and goes back. Then you have another transmitted one, and you have, after the production of this object, echoes in the gravitational waves. Normally, the time scale of this echo has the logarithm. So even if the difference from the Schwarzschild horizon is tiny, this logarithm makes this time scale observable. This is the key point why these echoes are very interesting. However, if you have absorption, if this absorption coefficient is not, if the reflection coefficient, sorry, is non-zero, in general, you expect that the echo has an amplitude which is damped with respect to the original one. But if you see the echo, you can even estimate how compact is the object, how far is from doing an horizon. But you see, with echoes even, there is a problem. And this is, I'm really closing on this. You see, with the echoes, of course, there is a question if you can use the standard ray optic approximation that people does to predict the echoes. And the answer is yes, the region over which they propagate is sufficiently long with respect to the typical wavelength of the gravitational waves we observe for being them considered high frequency. So you can go with an echo approximation, but there is another problem. Imagine you have an ultra compact object. You have the gravitational wave incoming, but then if you are very close to form an horizon, the way the rays escape is this exponential peeling close to the surface. This is a generic behavior close to the event horizon of a black hole. Now, this means that low energy density goes in high energy density. So by the upshot, what it is, if you have an echo and you have an ultra compact object, the ultra compact object have to expand very rapidly to not form a black hole horizon once you plunge energy into it. In order to do that, it needs to have a huge back reaction. And this is possible because a low energy density goes in high energy density. However, it means that the standard treatment of echoes that you have so far, which is to propagate these gravitational waves on a fixed background, their linear perturbation, does not work. You enter in a non-linear regime. So we need to go beyond the linear description, most probably, for ultra-compact objects like quasi-black holes.
So can I ask one question?
I'm closing.
Ah,
sorry.
Just one question maybe from the audience on the last slide, where there was the delta. Could you remind people about the meaning of delta?
Delta is is here, sorry. Delta is defined here. The radius of the object is the Schwarzschild radius times 1 plus delta. The compactness instead is delta over 1 plus delta. For delta much less than 1, for an object which is ultra compact, then the compactness and the difference with respect to the delta with respect to the Schwarzschild radius are basically the same.
Thanks. Okay.
There is also a question by Carlo. I don't know if I should finish the talk or take the question.
So maybe you finish first and then we take further questions.
So this is just to say that I'm not saying that the echoes are not a viable channel. I'm just saying that we may need further investigation if we want to understand this to rule out ultra-compact objects like this. Wrapping up, basically what we can say nowadays is that if you have a regular black hole, for example, you can have you can do some constraint already now with the electromagnetic signal from re-emission of light. The shadows, you need to know the model if it's predicting or not a very large deviation, sufficiently large deviation from the standard GR geometry between the horizon and the light ring, basically, if you like. In other cases, for example, we cannot cast constraint where you see the red cross. Okay, so the takeaway message is that it's not completely hopeless. So these are objects that somehow can be motivated through quantum gravity, although we haven't exposed a particular model of quantum gravity. And there are also models of quantum gravity where you can, as I was telling you, you can give up just in a tiny region regularity, and for example, avoid the short time scale stability of regular black holes. So this is why it's still worth looking at constraints on regular black hole. So my closure is the following. Black holes are basically the Rosetta Stone of gravity that we understood pretty well, but they are now even the new frontier for testing classical gravity. The point I'm making is that it's not completely hopeless that we can do quantum gravity phenomenology by observing black holes. The standard law that you can take care of the singularity of whatever is inside the black hole and just forget about it. Quantum gravity will deal with that and nothing will happen to the black hole. It will be equivalent, completely identical to a GR black hole. So all the observation regarding black hole cannot say anything about quantum gravity. It's based on assumptions. This assumption can be true or cannot be true. This kind of analysis that we saw today, it seems to suggest that long-range effects in space or time are rather than special, rather generic. It's more easy to have this long-range effect than do not have them. So the point is that can we constrain them? Can we exclude that they are there? At least we will have learned something about what gravity does behind the curtains of the horizon. Thank you.
Thank you very much for this interesting talk. So I think there are several questions. So let's start with Carlo Rovelli.
Ciao, Carlo.
Ciao, Stefano. Thank you very much. This is super interesting, and I could not agree more with your your final conclusion. I think we've been studying bouncing black holes for years now, and we have exactly the same sentiment that this is the case. But I have a technical question. I mean, you focus on all the phenomenology, which is for me super interesting. I've been focusing on what quantum gravity can say, the kind of quantum gravity we do, look quantum gravity, and I have a difficulty of fitting the scenario that we have from look quantum gravity in your list, and I don't know if I'm misunderstanding something you say, or I mean, it would go in the bouncing, I suppose, case.
Your scenario,
but,
I think that
let me make a specific question.
Yes. Not necessarily. Well, this is, for example, a scenario is close to what you do. It's not exactly what you do. You have here a kind of diamond-shaped region outside of the horizon, which is the non-classical region, right? And this is a paper you did with Massimo Bianchi. Can't remember now on the top of my mind of the other authors.
Right, but
And you have a non-classical region where basically you don't have a well-defined space-time there. You don't know what it is, you don't know, but it's a finite region of the Planck size, which was the point I was making, that
That's
you
right.
can avoid some of the problem. And other things that you do in another paper is that basically you have a situation where you cut here, you glue this part with this part. So you have basically a sudden change from trap to anti-trap, and this gluing here is basically your quantum gravity transition. So again, what you're paying a price that I wasn't paying in this analysis because it was simpler. You're paying the price that you have basically a layer where you really need discrete space-time description. You cannot go for a regular space-time. You don't have well-defined geometry where you cut here and glue. But your gluing avoids the stability of the inner horizon I was talking about.
That's right. But let me specify the point. We have a technical result in classical general relativity, which allows all that. If quantum gravity allows a transition in a small compact region, which sort of leaks out of the horizon just a little bit, then classical general relativity allows a solution all around it, including the trapped and the anti-trapped region, the black hole and the white hole. So that's where I get confused. It's not true.
It's this one. It's the bounds. No, but that is another one. It is another scenario yet. I think it's the scenario that is depicted here. This is a scenario where, okay, you need basically to have violation of the energy condition because you want to anti-trap. At some point you have to violate
exactly.
That's
a quantum
so
region. But the point is that outside it is an exact solution of the Einstein equations.
Except for a tiny region, which is this one, because you have to glue a black hole with a white hole. And if you remember, we even had the discussion in my office about that. You have a tiny region outside.
That's right.
And you can see that because around the black hole, you have the peeling that is the focusing. Around the white hole, you have the focusing, and you have to glue them at some point. So you have a tiny region where outside of the horizon, where you don't have a classical solution. But this is a great opportunity to do phenomenology. Because it depends on your model, how large it is.
Right. Well, what we don't know, and that's what we're trying to compute using loop quantum gravity, is whether to allow this, you have to wait for the black hole to have evaporated down to Planckian size, or it can happen before. That's a calculation that we're strongly trying to do, right? But the beauty of this is that
if it is m squared of m cube.
Or m cube, exactly. That's the question. But the beauty of this is that let me take the m cubes. M squared is more interesting, obviously, but let me take the m cube case for a moment. You just have a correction in where the curvature is Planckian, and then everywhere outside is just classical Einstein equations, and it works, including so it's a strange thing that you're locally isometric to, say, Kruskal, but not globally. So you can have a white hole in the past of the black hole with the same outside, which is just a Schwarzschild outside. This is a rather surprising result in classical GR that I think is unexpected, changes a little bit the way. And the point is that it's a topological thing. I mean, if you start with R, theta, phi, and t coordinates, you just don't get it because you have two spheres with the same R, 2 points with the same R, the same theta, and the same phi. The radius goes down and then comes up, right? So you cannot get it by cutting and gluing. You cannot get by take a piece of Kruskal. You have to take two and cut in a funny way. So I just wanted to.
And I think that is a very interesting case. You see, this analysis implicitly, I don't want to put my personal bias beyond the results, but my personal bias is that this analysis is strongly suggesting that somehow the bounds maybe, now you're converging on a bound which is basically at the end of the evaporation, if I understand, right? The last version.
Well, we don't know.
Basically because it's after m cube.
That's what we're trying.
The fast bound.
If so, there's no m square. It's a pity because we have much less chance of seeing it. But there is some phenomenology there as well. And that's far from established, and that's why we're trying to use loop quantum gravity to actually compute. Instead of saying, well, quantum gravity might do this and that, just compute it.
Exactly. So
within a given
that is the relevant question that quantum gravity at some point should answer, Because if we have the typical timescale of this bounce, and it ends up to be, see, if it is order m, I think the only way to make it compatible with observation is that the story of multiple bounces that stabilize on an ultra-compact object, then you have the constraint on quasi-black hole. But if you get m squared, then we are in business, and then you can do observation, which are very interesting from the point of view of the electromagnetic and gravitational space. You can really use multi-messenger astronomy, because primordial black hole would do the bounce now. So if it is m cube, then for large black hole is larger than the life of the universe, as you know better than me. So then observationally,
well, they're the primordial
exactly.
black holes.
Then, exactly, but then probably you end up casting constraint on the population of primordial black holes if you don't see really a candidate observation, right? M squared, it would be much more exciting.
No doubt.
I don't need to convince you. Okay.
No doubt. But I don't lose hope. Also, I mean, I don't want to monopolize that.
I was waiting for you guys to make this calculation and prove it.
Okay, but I was saying that even with m cube, you know, let me put it this way: the trapped photon are still coming out at some point.
Yeah,
it's very short the lifetime inside, right? That's the point. They come out immediately from the point of view of, if I can say that, of the photons.
And there is a very interesting discussion that would open up, but probably is for another occasion, about the information loss problem, because there is people that do not like this. They say that there are, you know, you cannot release the remnant at the Planck scale, and that wouldn't solve the information loss problem. But the bounce is, you have to analyze it and take into account the different time scale of the photon and of the stereo. So it's an interesting discussion. There is a discussion, in fact, also in your paper about this, but I mean, probably it's for another time.
Okay, I think we should turn back to the more technical questions, because there are some other questions. Thanks so far. So there's a question by Uwe Fischer. Can you ask?
Hi, Uwe.
Hi, ciao, Stefano.
Nice to see you.
A long time that we didn't meet each other, unfortunately. I hope it will soon be again. Okay, so you mentioned analog black holes in the beginning.
Yes.
Can analog black holes tell us anything about resolving the black hole singularity? I mean, the Einstein equations, what you wanted to give up, are not holding by default in analog black holes. Maybe some one-loop correction due to Sarov-induced gravity, but we are given it for free that the Einstein equations do not hold in black holes. So can black holes in the analog context tell us anything about resolving the singularity problem?
Well, okay, you see, in analog gravity, you have the power. You're basically God. You can play God, and you can decide which spacetime you want.
But that's why I like
from
it.
The point of exactly. So the problem is, from the point of view of you can simulate the singularity, but you cannot really say that you can resolve it, because of course, you take a Bose-Einstein condensate. You can do an acoustic black hole in a Bose-Einstein condensate, and you can even simulate a singularity, even without throwing out atoms, even conserving the number of atoms. So from that point of view, you can simulate singularity, and you can say what role do they play. And there is an interesting comment I would like to make, because recently we look basically what happened to Hawking radiation in acoustic black holes in Bose-Einstein condensate. And in principle, you know that in a Bose-Einstein condensate, Hawking radiation cannot, for example, lead to any information loss. It's a perfectly well-defined quantum system. So if you look at the atoms there, even if I simulate a singularity in the sense of a region where the hydrodynamic limit is not well-defined, so in a sense, space-time is not defined, I still have the atoms. So if I describe the physics at the level of the atoms, nothing can be lost. Nonetheless, if you look at quasi-particles...
Well, the quantum many-body state of the atoms is given by the parameters.
So, exactly. So what you can see, you can show that there is no information loss in Hawking evaporation in Bose-Einstein condensate, but you resolve it if and only if you take into account that the evaporation generates correlation between the matter, the quasi-particle that would be the analog of the matter propagating on space-time, your Hawking quanta, they correlate with atoms in the condensate, which are the building block of your space-time. So there are correlators which are suppressed like 1 over the number of atoms in the region of the black hole. So as the black hole squeezes, and in some models of analog gravity is really squeezed by evaporation, you can prove it. Then what is happening is that these correlators between the atoms of space-time, the discrete structure, the fundamental Hilbert space, the fundamental degrees of freedom accounting for your fundamental Hilbert space, are these correlators are recovering the whole information, and you have a basically unitary evolution, and everything is fine. But if you decide to go to the classical limit, you replace quantum spacetime by a classical spacetime, then you have you lose these correlators and information is lost. So here the simulation of a singularity in analog gravity is teaching you that the information loss problem could be a semi-classical gravity problem. It's due to the fact that our obstination to solve it by having a classical spacetime. Now, if you have a model of quantum gravity that for which there is a unique Hilbert space for gravity, for matter and gravity at the fundamental level, and I think, I don't know, this is something that I would like to ask the people working in for example, quantum gravity, if they think that there is a unified Hilbert space subtending the whole structure, because of course you're not putting matter for the moment, but I would find very difficult to imagine that at the fundamental level there is a theory with gravity and matter which are always separated. They live in Hilbert space that are just factorized. Now that would be strange. But if there is a unique Hilbert space, the evolution is unitary on that Hilbert space. It's only when you insist to forget one Hilbert space to make it classical that you lose these correlators forever, because you basically replace an operator by C number.
It's similar to an open system approach. You trace out 1 degree of freedom and
exactly, and then the information loss is due to the fact that the Hawking partners that fall in the non-hydrodynamic region, you basically cannot account for. They become out of space-time in your language, and you are not able, you trace over them, and then you have the information loss. But that is a semi-classical problem. It's not a quantum gravity problem.
So would you think it relates also to the quantum back reaction problem?
Yes, it does. In fact, if you can show that the squeezing, you can do also in analog gravity a back reaction calculation. Of course, it's not based on Einstein equation. It's based, so it's more model dependent. But for a canonical acoustic black hole, you can show that Hawking radiation squeeze the black hole, make it smaller and smaller. And what is happening is the number of atoms in the black hole are less and less. And what is happening is that these correlators between the number of atoms in your analog spacetime and the Hawking quanta are becoming more and more important as the black hole evaporates. So
is this in your paper with Andrea Trombetoni, which I read?
Yeah, in the last 2 papers I made on analog gravity. But you see, it's really, I think it's based on the idea, if quantum gravity has a unique Hilbert space for gravity and matter, then in a sense, I think it's a general lesson. So, at least I wouldn't pose the information loss problem like people sometimes does in semi-classical gravity. I think that is an ill-posed problem. You need quantum gravity from that point of view. You need to really track the degrees of freedom. The Hawking partner, when they fall into the black hole, they go in a quantum gravity region somehow. So a possible answer is that you need to have the tracking of them. You need to account for these degrees of freedom all the way through.
So what would quantum gravity for you be in the analog context, if anything?
For me, in the analog constant, quantum gravity is the full theory of the atoms. It's the many-body system of the atoms that are forming both the fluid, that the quasi-particle. They are all expression of the same substratum. And this fundamental substratum basically is accounting for everything. Of course, it's a very simplified object. It's a toy model, and quantum gravity will not be that simple. But the basic idea is that you need to evolve things in the full Hilbert space to see the unitary.
The basic idea is that you have unitary.
General lesson.
Yeah, the basic idea is that you have some model of unitary quantum evolution. Yeah.
Yes, at the fundamental level, on the fundamental Hilbert space, that from which from the fundamental quantum theory, from which you have on one side the classical spacetime and the other. Normally, we have classical spacetime and quantum matter. You need quantum spacetime as well, and you need how the two things correlate in order to solve the information loss problem.
So maybe as a matter of fact, since we have only about 15 minutes left, I would really like to open up the discussion again for so that we can address both speakers with your questions. Or maybe Francesca, you want to comment on the last question still, or? No. Okay, so then maybe we...
Yeah, I very much, I was cheering and didn't interrupt what Stefano was saying.
Okay. So then maybe we can start with some more general questions now to have the last couple, well, we have like 15 minutes, I think. So I have here Daniele Oriti, you want to ask something?
Yeah, in
Hi,
fact,
Daniele.
it's a, hi, Stefano, hi, Francesca. In fact, it's a further comment on the last point made by Stefano in reply to the last question. I agree with the picture that Stefano was suggesting. I just want to comment that when you go to the full Hilbert space and you are in a fully quantum gravity context, the tricky aspect for realizing concretely the solution that Stefano was suggesting is to define what you mean by the unitary evolution for the full set of degrees of freedom, because the same quantum gravity setting that will lead you to change picture out of the semi-classical one will in general not allow you to have a temporal direction with respect to which you would define unitary evolution for the fundamental degrees of freedom. If you manage to have that maybe as a first step in the approximation leading you to the full physical description of black hole evaporation, then the solution of Stefano, suggested by Stefano, would apply, because indeed you would have correlated degrees of freedom between the sector of the Hilbert space that will give rise to matter and the one that gives rise to the effective space-time description.
So what is replacing time? Basically, what you're saying is that what replaces time in a setting which is fully quantum gravitational, right? So you don't have, what is the analog of the Hamiltonian operator, if you like? Well, you evolve states.
With respect to which you would define unitary evolution, yes. So there should be, I mean, somehow if I read your suggestion coming from semi-classical gravity, then you're saying, well, at some point, the whole distinction between space-time geometry degrees of freedom and matter degrees of freedom will have to be dropped. I agree. But then for running your solution, you're still holding to a notion of temporal evolution for both sets of degrees of freedom, which we know, if you go truly fundamental, will also have to be dropped.
Yes, yes, of course.
So there are both steps that need to be accounted for in the full theory.
Sorry, the advantage of working with black holes, I mean, you can ask the similar questions for cosmology, but the advantage of working with black holes is that a black hole is limited to a finite region of space-time, and then the surrounding can be treated as classical, and the surrounding you can have well-behaving clocks, isn't it? So Daniele or Stefano, doesn't this create a way out?
Well, you're right, but the unitary evolution is also for the degrees of freedom that form the black hole. So you cannot just rely on. It's not obvious that you can use the same notion of time that you use for the exterior classical region. May work.
There must be some kind of order
parameter,
no? There must be some kind of order parameter. If I mean, somehow space-time will be emerging from the fact that you have an expectation value of some coherent state of some geometrical operators. And then when this coherent state is very highly populated, you go toward a continuous and classical limit, I would expect. So there must be some notion of how the evolution of the fundamental quantum Hilbert space works, right? It will not be the time of the emerging space-time, that I agree.
Exactly. So what you were using as time to define unitary evolution is itself an emergent collective effect of the fundamental degrees of freedom, where you were mixing matter and space-time degrees of freedom. So I mean, it needs some work to show that such a notion emerges in the way to apply your strategy. But I agree with the general scheme for resolution.
Okay, so I think there is another question by Zahan. Zahan, can you ask?
Yes, I was looking for the button. Okay, I have another question from Francesca. It is the same question as I asked, but I wanted to ask it in another way. I mean, if you you said that you'd say you associate a bouncing universe to a universe which has a superposition wave function. Yeah, that's did I understood you correct?
Yes.
So if the universe has a superposition, you consider that there is some actual universe which is contracting and then expanding. So you somehow you go beyond the wave function. You consider that's the wave function, but beyond that there is also some actual universe, some actual geometry for the universe. Is it correct?
Well, like every quantum system, the universe experiences different regimes. There is a regime, the current regime that we are experiencing is one in which we have an expanding solution and the universe is behaving classically. The idea is that there could be also, so then if you go back in time, because the universe was small and dense, we think that the universe was experiencing a quantum regime in which quantum gravity governs the universe. The idea is that there could have been also a precedent, a previous phase of the universe that can be treated also classically. This is what you obtain in the simplest model. There are also other possibilities. I think Stefano, together with Emanuele Lesci, for instance, studied a universe that was oscillating, staying always staying in a quantum regime, and then starting an inflationary space. But the bouncing one, whether you by the way, also in this kind of scenario, you have the possibility to take a time reverse solution with the bouncing. I mean, it's the opposite. It's collapsing and bouncing, or oscillating many times, and you can join the two solutions. So. Okay, so in the simplest scenario, you imagine that you could have a previous classical universe. And then there is a region that is a quantum region that connects the two classical regions. And this region is a region in which, well, you can think that there is a bounce. In fact, in the approximation that is typical of cosmology, you can also continue the trajectories through the geodesics through the bounce. But a powerful way to see what is going on is to think in terms of a quantum tunneling. So the quantum tunneling is a process in which you go from one classical solution from another classical solution through this quantum region, in which you have a superposition of the two solutions. So you can think of the quantum regime of the universe as being a place in which there is a quantum superposition of geometry. Now, say that quantum gravity applies within the universe, not only in this peculiar case, in the sense that we can also go in the lab and we can see superpositions. I mean, there are now ideas about how to measure superposition of different space-times. So I don't want to give you the impression with my answer that the only place in the universe in which you can have superpositions of geometries is in the early universe there. But so the universe, the most general state of a quantum geometry is a superpositions of many states. And this is something we can even experience possibly or hopefully even in the lab.
Okay, Thank you. But maybe the question is also about the foundation of quantum mechanics, whether or not one can understand superposition of a macroscopic thing. I mean, just like superposition of a dead and a live cat. I mean, that's comes down maybe to this question, which in quantum mechanics also cannot be understood. A cat being dead and alive at the same time.
Oh, I think it depends on the interpretation that you take of quantum mechanics. There are.
I didn't mention any interpretation. I just mentioned about a cat, and I have never seen a cat alive and dead. I understand that if one wants to go give an answer, then one needs to take a position about interpretation of quantum mechanics. So, but
I think that your question was not associated with interpretations. It is a concrete question of whether we can see or not macroscopic things in a quantum superposition. And this question, I mean, in the lab these days, we are making people in experimental quantum mechanics are making miracles. I mean, they can even make in a superposition big things like a virus. So that's just a matter of technology, and one has to fight against the coherence, of course. So in order to see quantum effects, one has to isolate some specific degrees of freedom and having a situation in which they don't interact with the degrees of freedom of the environment. That's the challenge. But I think this is possible. And for quantum gravity, as I was mentioning, there are ideas about how to see these kind of things even in the lab. And so the question is not only about being in a situation in which we have a very high energy density, but there could be also other situations in which the combination of different parameters that governs the dynamics of my system can give rise to observable quantum effects.
Okay, thanks.
Okay, so since we are already short of time, so maybe there's time for one or two final questions. Stefano, you have still time? Yeah, let's have one more question, which is here for a long time, by Julius Dobosevsky. So maybe let's have this.
Hi, yeah, thank you, Francesca and Stefano, for really fun talks. I have a question to Stefano. It's about, so I know that the regular black hole solutions can have very different cores, in the sense that we can have asymptotically flat a core of a regular black hole or asymptotically de Sitter core of a regular black hole. And I wonder whether those do differ significantly when it comes to their fine-tuning and stability, and B, whether we could try to distinguish between these two using the sort of phenomenology you described.
All the black holes that are regular have the stability I talked about, because basically you have, think about it, you have basically a function that should become 0 at one horizon, then is negative, and then it needs to become again positive in order to untrap, to close the trapped region. So basically you always another place where they always come in couples, the zeros. So if you don't have a wormhole, an inside wormhole, and that is the problem, right? Because then you have always an inner horizon. This inner horizon structure is always leading in all the model of regular black hole. You can explicitly do a numerical calculation of the perturbation, and you see that there is always an exponential growth of this perturbation. In some models, this exponential growth is for a finite time, and then you have a polynomial growth, but those models are still very unstable because the exponential growth lasts enough to destabilize the structure. So regular black holes, if they have this inner horizon, are unstable. And that is a very interesting result, because it tells you that a very reasonable candidate, in a sense, is you have to run against this instability. Not only, but they cannot evaporate completely, because as you see the inner horizon, it tends to grow. The outer horizon, it tends to shrink. When they touch, the surface gravity is basically 0. So in the Hawking evaporation process, the surface gravity is going to zero as the region evaporates. So you are competing with this. You see, you are competing with the fact that you are switching off Hawking radiation. So somehow you have to open the regular black hole by something else than Hawking radiation if you want them to be not everlasting. So there are problems in there. This is why, you know, personally, I think that the bouncing resolution or the interior wormhole, but the interior wormhole has the problem that you need really or to change topology, which quantum gravity can do, and then you tunnel to another universe, or you have these non-analytical points, like it was showing in one of the resolution, if you want to avoid the topology change. So that's, but the stability of regular black hole, I think, is now understood that is ubiquitous.
Thank you.
Thanks. So let's take one final question by Uwe Fischer.
Oh, it's more like a remark. If one considers the superposition of space-time geometries, the quantum superposition of space-time geometries, I mean, this is natural in the context of quantum many-body systems because they have been observed in the lab. I mean, quantum superposition of macroscopic objects, and if these macroscopic objects can by themselves constitute space-time geometries, like what is natural, at least in analog gravity, then quantum superpositions of space-time can be realized in the lab.
Yes.
I mean, this is just very plain like that.
Yeah.
Can you just say which experiment shows the superposition of macroscopic objects in lab? Just want to.
Well, I mean, there's many photonic Schrödinger cat experiments, and I mean, if you believe that a squared, this quantum superconducting quantum interference device with a flux qubit is also a Schrödinger cat, which, well, let's say many people do, then this is also such a observed Schrödinger cat. And if those two counterpropagating Kubo pair flows each constitute a spacetime, then that's a quantum superposition of spacetimes in the lab.
Okay, so maybe I think we are already several minutes over time, so I think we should stop here and thank all of you for that discussion, and thanks very much for both of you speakers for the very nice talks, and thanks to the audience also for being here. Yeah, so I will hand over just to Ward, who will announce the next session, and I hope to see you again here all very soon. Yeah, Ward, you're still muted.
Yeah, thanks. So Stefano, Francesco, many thanks for these interesting talks, and thanks the audience for all the discussion. So next time we're going to have a session on the future of quantum foundations, and Siran Das and Sandro Donati will be speaking, and that's going to be on the 1st of July, so next month. So thank you all and goodbye.
Thank you. Bye.
Thank you.
Bye. Thanks again for having me.
Thank you.
Our pleasure.
Yeah, it was a big pleasure for us as well. See you all again. Stay healthy.
And thank you, Stefan, as well.
Mille grazie.
Grazie tante.
Grazie entrambi.
Okay.
Bye.
All right. Thank you. Bye, everyone.
Bye-bye.
Bye-bye.